Today is going to be a review day, so we're going to work a few problems from your homework. You may have already done some of these. That's okay. You can at least check your work, and I'm going to help you through a few of the problems. Number 8 on lesson 7.4 is actually one that looks rather difficult, but if you're just changing from rectangular to polar form, complex numbers, it should be pretty easy. You don't have to graph them out, but I like doing it just to make sure that I'm on the right track. We will go square root of 3 over 2 to the right and 3/2 up. Those may not look like anything to you, but that's okay. We're going to just go ahead and label them, and then we can use that triangle to figure out what we need to find out. So we can use the Pythagorean theorem to find out the modulus, and then of course use the inverse tangent to find the argument. So let's go ahead and square these. This is just the Pythagorean theorem. 3/2 squared plus square root of 3 over 2 squared. And of course that will equal the modulus squared. I'm just going to label that M for right now. We a lot of times label it R. But that's 9/4 plus 3/4 equals M squared, and of course that comes out to 12 over 4, which we can reduce to 3 equals M squared, and so M equals the square root of 3. Now the whole idea is we're just going to convert from rectangular to polar. All we need is the modulus, that's square root of 3, and then we're going to write cis, and we need that angle. Once again, we can use the inverse tangent to find that angle. So we'll say the tangent of theta is equal to 3/2 over square root of 3 over 2. You may notice that you can go ahead and multiply this by 2 over the square root of 3, both the numerator and denominator. That's how you flip those back to the numerator, and you'll notice it just comes out to 3 over the square root of 3, which is of course 3 square root of 3 over 3. You don't even have to punch that one into your calculator, because you may recognize that this works out to the tangent of 60 degrees, because you recognize that the square root of 3 is the tangent of 60 degrees. Hopefully you recognize that, and this works. Of course, if we wanted it in radians, that would be square root of 3 cis pi over 3, and that would work as well. Once again, the idea is to simply use the Pythagorean theorem to find the modulus, and then use the inverse tangent to find the angle. If it's in a different quadrant, you may have to add or subtract from 180 or 360 in order to make it work. Look at number 20 on 7.3. That one may look a little bit odd because it's written all the way out. In fact, most of these are. They're written 4 times the cosine of 1 plus 5 plus I times the sine of 1.5. But hopefully you recognize that form as simply the cis form, the abbreviated form. So 4 cosine plus I sine of 1.5. And then it says divided by a bunch of other stuff. That would simply be 8 cis 0.8. Of course, these are in radians. That might make it a little bit more difficult for you, but hopefully not. This is converting from polar to rectangular, and dividing in polar form is very difficult. However, dividing in rectangular form is really easy, so go ahead and work this out. And the easy way to do it is to think of it in terms of cosine plus I sine. So really, you're going to multiply 4 times the cosine of 1.5, and then you're going to multiply 4 times the sine of 1.5. Make sure your calculator is in radians before you do this, but then you can just say 4 times the cosine of 1.5. That's all you've got to do on your calculator, and you get 0.28. That is the real portion of this. And then you go ahead and do the imaginary portion, which is 4 times the sine of 1.5 if you're in radians, and that comes out to basically 4. So that is plus 4i. You're going to put all that over 8 times the cosine of 0.8. That comes out to 5.6. and then 8 times the sine of 0.8. That will come out to 5.7. So that is plus 5.7 I. Now you can easily work this problem using conjugates. I'm not going to work the rest of it out for you because you can do that yourself, but it should be a really simple problem. Now just find the conjugate of the denominator and multiply. In 7.4, we learned how to do DeMoivre's theorem, and we're going to apply that on a couple of problems here to find the roots of complex numbers. First of all, you'll notice this is already in polar form. That's good. We can only do DeMoivre's theorem in polar form, so we need to go ahead and write it out as a power instead of a root. Of course, roots can be written once again as fractional powers. And now we just do DeMoivre's theorem, and we're going to once again leave this in polar form. So we go ahead and we raise 125 to the third power, and hopefully you recognize that as being 5 cis, and then we multiply 4/3 or 4 pi over 3 times 1/3. So that comes out to 4 pi over 9. And so that is our principal root. That is the first root. It's the principal root. Now let's remember, in order to find the other ones, we could take our original number, add 2 pi, divide by 3, or we could do the same thing of just adding 2 pi over 3 to our last answer, which is 4 pi over 9. Hopefully you can recognize that we'll need to get a common denominator here. That common denominator will make this come out to 6 pi over 9, because you just multiply both of those by 3. So we're adding 6 pi over 9. And once again, that's 10 pi over 9. I'm just going to work with the angles for right now. And then we'll add 6 pi over 9 to that, which comes out to 16 pi over 9. Both of those have the same modulus and have different arguments. If you added one more time, you would be over 2 pi. But once again, here's the review. The idea is that you take it in polar form, you rewrite it so you can do DeMoivre's theorem, raise it to the power, and multiply, and then to get all of the other roots, this number is the key. That's 3. That means we're going around the circle, then dividing by 3. In other words, we're adding 2 pi divided by 3. I used the common denominator form of that, 6 pi over 9, in order to add to our answer to get 2 more answers. And those are all of those roots. I want to work number 14 with you for a couple of reasons. First of all, because it looks a little strange. If you notice, it's just cis 65 degrees. Hopefully you recognize that that means that there's an understood modulus of 1. So when we rewrite this one as 1 cis 65, we now raise it to a power of 1/5, and we can do DeMoivre's theorem. This one's really easy because any power of 1 is always 1, whether it's a fractional power or a whole number power, it doesn't matter. It's going to come out to 1. And then, of course, we divide 65 by 5. That, of course, comes out to a 13-degree angle. That is, once again, the principal root. DeMoivre's theorem is really easy. However, finding all of the other roots may seem a little bit more complicated, but it's not. Remember, we're adding 360 each time, and then we're going to divide by 5 again. So we're adding 360 over 5. You're going to learn these numbers pretty quickly, but when you divide 360 by 5, of course, you get 72 degrees, and that's what we're going to be adding to each term. So we're just doing this over and over and over. So 1 cis, and then we add 72, so that comes out to 85 degrees. And then add 72 to that, and add 72 to that, so we get 157 degrees, and then 229 degrees, and then 301 degrees. If we did it one more time, it would come out to 373 degrees, and you recognize that doesn't work. Each of these has the same modulus, so we write each of them 1 cis whatever. Here's the principal root, all of the other roots. You've got the rest of the class period to work on your homework that's due Thursday. Hopefully you've already got a good chunk of it done, but remember you need to do 7.3, numbers 1 through 20, and 7.4, numbers 1 through 15, just the odd problems. Have those done and ready to check in class on Thursday.